Okay, hello everyone. Welcome to our EE321 Term Project presentation. Today, me and my teammate Tayyib Shah will be talking about our term project for this semester regarding the Zoom robot, and we'll be talking about what our project has been about and our project designs and what we have implemented uh, programmatically in implementing the robot logic. And we've gone over each step in detail in this presentation. So we can start moving forward. So first things first, the Zoom robot is just basically kind of a robot that's built with Arduino. It's just basically a robot that will be scanning its surroundings and reporting the amount of objects it sees. That's the point of the project, more or less. And the key idea of this project is making sure that we are able to program the counting logic in such a way that it's not undercounting or overcounting the object the robot is seeing. So we can start by moving forward and seeing what we have tried. And first things first, I want to talk about what's actually making the detection happen. So there is something called a reflectance sensor, and that reflectance sensor, I mean, there are several of them more so. The reflectance sensors are designed such that the robot can detect changes in color between like on the arena it will be placed inside, and those changes will make sure that the robot will stay confined in the inside of the arena it's contained in, because the arena will be made in such a way that the perimeter of the arena is going to be white and the interior of the arena is going to be black. So if the robot is going to go to the edge of the arena, it will detect a major change in color and it will not be able to cross over. And we'll be implementing the logics in such a way that it will not cross over. You will see that shortly. The infrared sensor, meanwhile, will be just for detecting the objects directly, because there will be objects based in the arena, and the infrared sensor will be checking for those more or less. And like I discussed earlier, Arduino, we are using Arduino to design the logic for this spot and the whole program more or less. So moving forward, we can now talk about what we're actually meant to do in this project. So the basic idea is just to implement accounting logic, and that's all there is to it more or less. And also, if we're going to be implementing a movement logic, to make sure that the robot strictly is confined inside the arena. And we're going to be testing if our program actually works using different scenarios, different objects, different object sizes, and different object placements. And we're going to make sure that these experiments are repeatable, meaning that it's not just like a one-off thing, more or less. So we can see further of what our approaches were. So we had three major approaches to designing the robot logic, each with varying levels of limitations, complexities, and errors, you can say. So the first approach, which we talked about, is more or less just have the robot start in a certain part of the arena, and it will start rotating and start detecting the amount of objects it's seeing. But the catch is that, unlike what you would traditionally think it to do, which is just to rotate once, count, and display, we wanted to make sure that there's not going to be any undercounting or overcounting caused by some object being placed like directly behind another object, which the robot will not be able to like differentiate between those two. So what we thought about doing was more or less, instead of having that process happen once, we're going to make it happen several times. And each time that happens, we're going to save the amount of objects the robot is seeing. And how we do that is basically we're going to be implementing an array. And my teammate Azhar Tayyib will be talking about that further. But more or less, the basic idea is that we'll be checking the amount of objects the robot is seeing currently, and then it will be moving in a straight path in some direction, it will start rotating and detecting objects again, and then to move again, detect objects again, and so on until at the final point it will stop finally and will calculate the maximum amount of objects it saw, and it will display those. Now, that was the original idea of what we should be doing, but we were not able to go with that, sadly, because it was too complex of uh, the implementation was too complex, more or less, and the movement logic was just too hard to go through. The second approach was more or less kind of the same, but instead of just moving forward, it will be moving in a circular motion. It was just to counteract the fact that the motion forward in the first approach was causing a lot of collisions and straying off the main path with the robot. So we couldn't go with that, sadly. But even with the circular motion, the collisions continued to still happen, and the error rate was still quite high. So we also couldn't go through with that. So finally, we kind of relented and decided to just stick to the simplicity of the project, and we just ditched the whole movement logic of the robot, and we just basically had it just rotate once and display the amount of objects, and that quite frankly was seen to be very sufficient for the purposes of this project. Now, we did not see major undercounting or overcounting happen with the simplicity of this approach. So, as my friend Clay will be explaining now, we'll be talking more further about the approaches we had with the coding and how it was actually implemented. And yeah, can have my friend talk about it now.
All right, thank you so much, Abdullah. So as Abdullah stated, like we tried the first two approaches, it did not work out due to the physical limitation of the Zoomer itself. Given its size, it is difficult to maneuver it between objects. So we went with, the simplest approach that we could find, which is keep it at one point, rotate it over there, and count. So that's what we did. Now, within the third approach, uh, we sort of divided the entire approach into two specific portions. Now, the first part of it would be stage one, which is the counting and blinking stage. In this stage, the zoomer will essentially spin in 360 on the spot and count all the objects that it sees in its vision. It would then blink its LED to display the object count. So, for example, if it's detecting 5 objects in its vicinity, once it stops, it will blink the LED 5 times. In the next stage of the operation, this same zoomer, without any external help, will seek these objects out and knock them over. Once it has knocked them over, after a set period of time which we decided, it will stop moving them at all. So our first bit, now I'm going to start explaining like the code and how we actually achieved our goals. The first bit was obviously the initialization and calibration of the zoomer. So first up, we defined all our variables that we would be needing. Like we defined which pin on the Arduino are we going to use for the LED pin. Since we're using the onboard LED, obviously we're going to use pin 13. Our sensor was connected to pin 6, so we had to define that. In the calibration bit itself, we use the built-in command in Arduino for calibration. And we calibrated it sort of on the edge of the arena on the white and black portions to help the sensors differentiate between the two. So when we start the computational aspect of our program, it will be able to tell the difference between the proper arena and the edge itself. Our next bit, however, was where things get interesting. So stage one, which is the count and blink mechanism. Now, there are many approaches to this. We tried a lot of different things, and it was where we felt like, this is our final product. This is where we kept it as simple as possible, yet achieving its goals. So basically, what we're doing is we're using like a bunch of variables, such as object count and count single. And when the zoomer is essentially spinning, right, it's going to spin for like a set amount of time to make it go in a 360-degree fashion. Now, this number that we found, we spin the zoomer for 2.5 seconds, right? This time was found through trial and error. There was no fixed formula for it. We tried like different times and different speeds, and this is where we found that okay, now it's spinning in 360 degrees. The actual computation of it is relatively simple, apart from one aspect. We just have a variable count object, or sorry, object count, and we keep incrementing it whenever it spots an object in its scanning stage. However, the issue here was, what do we do about different sized objects? So for that, we use a condition called count single. How this condition works is basically we start off with a false condition, right? When it detects an object, this condition gets triggered. It becomes true. However, we don't increment it just yet. Once it becomes false, again, once it sort of crosses the object, that is where we increment our counter. So what this does is it basically does not care how big the object is. It will only increment the count after the object has ended. So that sort of helped us get over the aspect of different sized objects. Had we not had this flag, we would have had a much more difficult time with the counting aspect, because once it starts counting, it would keep counting at an errorless in an errorless manner, right? So once the counting element is done, then we have obviously the LCD blink part, which isn't really difficult. It's a simple if statement using I as sort of a counter. And for every object that it detects, our Zoomo detects, it's gonna make the LED on for 0.5 seconds and then turn it off for 0.5 seconds. So you have like a noticeable blink that we can like actually keep track. Once this stage was done, we moved on to the second stage, which is the movement aspect. Now, this is much simpler than what we previously had in the count and blink stage. In this stage, all we're doing is basically whenever we have like a default stage where the Zoomo is rotating, like in the turn right object. It's going to be rotating and searching for objects. When it detects an object, this movement mode changes to go, as you can see in the code right here. In that go stage, it basically just goes over and knocks the object over. Once the object is removed from its field of vision, it goes back into its searching state. Now, the only thing that we had to make sure in this particular part of the code was to make sure that the Zoomo doesn't fly off the edge of the arena. So for that, we use the calibration aspect of our experiment, which we did at the very beginning. And all we did was assign a variable leftmost sensor to it. And whenever it detects the edge of the arena, it sort of not only does it go back, it also slightly turns. So it sort of repositions itself for like 0.5 seconds. That allows it to get back into the arena and back into its normal stage. Now, once we have all these stages set up, now this is the important part, because individually those stages were working, but combining them proved to be a bit of a hassle for us. So what we did was we implemented flags. And it's not like a Boolean flag, it's not a 0 or 1 flag. This is like a multi-stage flag. So it's relatively simple. What we're doing is we're starting off with flag 0. That is our count stage 1. Once it begins, it's going to be at flag 0, so it's going to enter the count stage. Now we're running this count stage for 15 seconds. That would allow it to spin, count, display, everything is done in 15 seconds. At the end of this, it's going to increment the flag. So now the flag is going to be 1. For flag 1, we assigned it to this seek and knock stage. Again, for 15 seconds, it's going to go into the seek and knock algorithm, which we defined previously, and it's going to go over and knock them over for 15 seconds. Again, once this is done, the flag is incremented. In our third and final stage, once the flag is incremented again, after 15 seconds, it enters our third stage, which is simply a pause mechanism that we have that would make the Zoomo stop in its track. That was pretty much it from the code itself. Now I believe it's time to show the testing mechanism. What we did was we set up the arena into 4 distinct tests. These tests were designed to like showcase the versatility of our project, to showcase that despite different objectives, despite different scenarios, the main objective of the Zoomo is still achieved. So begin with the first test. This is a standard edge state placement. As you can see, the objects are on the edges of the arena. We're gonna have like 9 objects in this, and apologies for that. I'm gonna have like 9 objects. So I just count them, display them as you can see right there. And now after 15 seconds have elapsed, it will enter, there you go, the seek and knock stage. As you can see, now that all the objects have been removed, it goes into its default scanning stage. And it will stay in that stage for 15 seconds until, there you go, it stops. Our next placement is a cluster placement. It's somewhat similar, but since objects are much more closer together, it gives it a very small margin for error between differentiation of objects. However, as you can see, it still works fine in this scenario. Nine counts, as you can see. And after 15 seconds have elapsed since the start, it enters the knock stage. Again, once all the objects have been knocked, goes back to its default stage. My apologies there. I miscalculated the time. I thought the time had elapsed, but it had not. So I had to wait for a bit. All right. In our third test, we have the decentered placement. So basically, we're not going to be starting in the middle of the arena. We're going to start at the edge so that we can properly test like the efficiency at its off-centered starting point. Like at the very, how well it measures the objects at the very end of the arena. You can see that slight reverse that the zoomer performs every time it hits the edge. Again, that allows it to recenter itself to get back into the arena before performing the rest of the function. And finally, we have our variable placement. Now for this, we had like 3 objects standing close together to imitate like one big object. Now, although we have like, how many, 9 objects in the arena, we combined them to make like 5 objects. And as you can see, the zoomer detects them as 5 objects instead of like 9 distinct objects or more or less. There you go. All right, then that concluded our testing stage. We tested like all the different aspects of our program. I'm going to hand over the stage now to my friend Abdullah for the closing remarks and conclusion.
Thank you so much, Tayyip. And yeah, that's a wrap from us, everyone. And I hope you enjoyed our implementation of the Zomo robot. And it was, in summary, we more or less explored several approaches, 3 to be specific, and we decided to stick to the simplest approach, like we said, and it worked out very nicely. And despite the fact that it has its own limitations in potential undercounting or so, it proved to not be that bad at all, and we were able to succeed in all of our experiments quite nice, as you saw in the demos that my friend Tayyip has shown earlier. And yeah, in the series of tests, we validated all of the performance of the robot, and we found it to be very satisfactory. And yeah, thank you so much, and I hope you liked the representation. We thank you all for your time in this course, and I hope you have a great day.
Thank you, guys. Thank you, Abdullah. Have a great day, everyone.